So this research is focused around the use case of pediatric asthma, which, as we all know, is very prevalent, causes kids to have trouble breathing, makes their airways swell, and highly associated with environmental triggers. And actually, the environment has a big effect on health. What we're finding out is that it's a bigger effect even than the genome. And the combination of the genome and the environment is really the predominant driver of the symptoms that people experience. So this idea about the exposome is sort of analogous to the genome, and it encompasses that whole life course of environmental exposures. And the environment includes things like lifestyle, socioeconomic status, and so forth. So it's often sort of partitioned out into things like the external environment, not only those exposures that we often think about, but things like the climate, the socioeconomic status, even stress and psychosocial factors are considered part of the environment. Then there is what you think of as sort of your local or specific external environment, so the things right around an individual person, cigarette smoke, the extent to which they exercise, maybe some infections. And then there's your internal environment, things like metabolic factors, your gut flora and inflammation, and these all come together under this big umbrella called the exposome. I forgot to warn you, I talk with my hands. So there's this whole field of study called exposomics that is the study of sort of defining these, what we call clinically relevant subsets of that overarching exposome. And there are a number of efforts getting funded nationally to start looking at some of these different types of exposomes, whether they're focused on prenatal period and early life, exposures and environmental things. There's a big program called ECHO that's looking at the effects of environmental exposures on child health broadly. And then our program is related to ECHO but focused on pediatric asthma and building out some infrastructure to do this research. So we know that air quality not only affects asthma, it affects a whole lot of different kinds of conditions. And as you've heard, off and on throughout the day-to-day, there's a number of studies happening looking at different kinds of conditions and the effects of the environment, from stroke and clots in the brain, lung conditions, things like depression and suicide, reproductive outcomes, early pregnancy loss, cancer, so a whole gamut of conditions. So part of our challenge, even though our use case is asthma, part of our challenge is to build out an infrastructure that can accommodate all these different kinds of problems. You all know about the Salt Lake City air quality, and we have this beautiful natural experimental conditions here, so we won't belabor that point. But one of the things that challenges us here is that we only have really 3 EPA stations, and so there's quite a bit of spatial gaps, and you know that the air quality around the valley has all these sort of microclimates and different aspects that aren't necessarily well represented in just the regional monitoring stations, and that's why we put these sensors out all over the place. So the idea of an air quality exposome is trying to get as much as possible a complete picture of those environmental exposures. So the idea is to combine information from wearable sensors, stationary sensors, those big regional environmental monitors, and combine that with physiologic data, symptoms, self-report data, medication use, clinical data. Well, all of these things happen in sort of different places and time perspectives. So from the idea of putting together all the data, it requires a fairly complex model of space and time, and the ability to accommodate things like mathematical modeling to fill in gaps in between what we can actually measure. So one of the first problems we ran into in thinking about this problem is that there are a whole lot of different kinds of sources of data that could be feeding air quality data into this platform. And not only is it just wearable and stationary, but no two devices, there are no actual standards for how the information looks, how the data flow runs. And so you compare any two devices and the data stream looks different. So with no standards and sort of no preset model for what are the data going to look like, we had to try to figure out how to combine this information together. And that's where PRISMS comes into play. So PRISMS is an NIH-funded initiative, and it's part of these larger programs like ECHO, looking at the effects of the environment on health. And in particular, we are looking at systems that include sensors, but are not limited to sensors for all different kinds of factors. And the program as a whole included a number of centers that are developing some novel sensors, 2 informatics platform groups, we're one of those, and then a data coordinating center. And so we all work together as a big collaborative effort. And then within you're not supposed to be able to read this, but this is just to give you an idea of the complexity of this project. So just within our center, we have a whole lot of sub-projects that come together in this program. So this is just our little corner of the pie, and each of these boxes actually has a bunch of projects like that. So on the whole, what we have one set of projects that's sort of looking at what's happening in the home. And if you looked at the posters, you saw some of the posters that show you some of the information they've got from some of the sensors out in the home and some of the experiments they've done with that. And following my talk, Dr. Meyer is going to talk about some of the interactions with parents and some of those interactions. So I won't talk on that. I will focus most of my talk on that sort of infrastructure, the modeling we had to use to try to figure out how to bring all this data together. And the scope of this is pretty frightening because the scope of the model has to accommodate everything from nanosensors to satellites, from physical and chemical to biological, from personal to the big broad sensors. And we have to somehow figure out how to model things out at this whole big gamut. So the idea is we're going to create a library of the different sensors. We're going to develop a means to store the data and the information about the sensors. That's what we call metadata. And then look at the quality of the data. So the process we used to do this was sort of a methodical stepwise process. We started with literature review. We looked at a little over 200 journal articles and extracted out as much as we could of the data elements. Mapped that out to sample data from all over the place, and you are familiar with many of these projects, things like Purple Air and Dr. Kelly's work. We've got some data from some epidemiologists in California and a number of different groups, and we tried to map it out to those actual data sets. And then the model was reviewed first by a number of local experts, and now we're in the process of reviewing it out with some of our collaborators across the country. And the slides will have a link if you want to get in there and actually dig at the model. But basically, it's divided out into these categories where we look at information about the instruments, the sensor themselves, what it's collected, how it's validated. There's information about how the sensor is used in a study, what we call a deployment. Knowing that sensors might be reused across different studies, and so it accommodates those. And then some metadata about the information that is spit out by the sensors and what actually we can look at from it. So then that all comes together in a big data integration platform, and the idea here is to try to start bringing in some of the national standards for information management and map it out to those, and be able to combine the sensor data, the mathematically modeled data, combine that with clinical data, self-report of symptoms, and associate that with some measure of our level of certainty around those data points. So some of the components in that infrastructure, we have a metadata repository. That's probably the most important component because that's what describes these non-standardized inputs. The ontology server looks at the naming across the different sources. And then we have an actual data store that is set up a little differently than we normally would set up a clinical data store, because we know that people move in and out of the area where sensors are, so we couldn't use the person as our core of our data store. We had to use just time, actually, as our core idea. And then an analytic layer, and I think you've seen at least one poster that shows some of the analytic modeling. This model and some accompanying ones are on a poster out there if you want to look at it, that some of our people like Albert are working on. We've spent quite a bit of time outlining out a bunch of different use cases. So because we're building a platform to support future research, we had to say, what might those future studies look like? So we've spent quite a bit of time with people doing this kind of research and trying to generalize out examples of different kinds of research that might run on the platform, and think about how those might send the information. So we focused on how the information would flow from sensors to either a mobile device or some sort of platform in the home, how that would come together across homes, and then how we might combine that with other kinds of data, how we might do things like ecological momentary assessments. So you can imagine a sensor having a spike in particulate counts triggering off a message to the server, which then texts the person saying, hey, the particle count has gone up in your home, are you cooking? And we actually have demonstrated that we can do that. And some of those so we think about how that information might have to flow back and forth in different kinds of studies, and then model that out in a formal way so that our software development people can actually tackle how to build something to accommodate those problems. We couldn't do this without a really big team, and this is only part of the team, but you can see the many kinds of departments that have had to come together to do this project. So I'm from nursing. We have biomedical informatics, our clinical and translational science department. We have pediatric clinicians. We have people from Electrical and Computer Institute, from scientific computing, chemical engineering, atmospheric sciences, bioengineering, mechanical engineering, software development people, and this is only like part of the team. So, questions? Look, I made it with 2 minutes to spare. Yeah! Questions?